turbofan efficiency technology that shows a double-digit reduction in fuel burn emissions. Please welcome Sander de Moor from deltaBurn.
Good afternoon, everybody. Everybody can hear me? Good. deltaBurn is a startup. We're trying to bring to market some really surprising technology, and let me dive straight in. So who are we? We are a research and development company, and we are active in supplemental type certificate production. We are registered in Singapore, and the aero products that we bring to market are meant to reduce our global aviation fuel burn footprint. Our mission is to drastically lower global aviation fuel burn, and by doing so, we are also trying to support the global SAF push. As you know, SAF is quite a huge target to achieve, and if we can reduce the fuel burn, we also make it more attainable. The number that we are proposing is 33% emissions reductions. So our technology will push a 1/3 reduction in global aviation fuel burn, and of course that translates one onto the other. In addition, by doing this, we're giving you a lot more range for your current aircraft. So 1/3. If I would say 1% or 2% or 5%, you might believe it, but 1/3 is a huge number in today's market. So let me explain. What we do is we make a modification to the jet engine. The engine you all know. As you can see, you have the front bit, the fan, and then there's the core in the middle, and then a lot of the air goes around the core in the bypass duct. So what we do is we increase the fan disk efficiency, the propulsion disk efficiency. We attach a very specific modification to the fan blades, and we make the fan blades a lot more efficient. There we go. And what we do we change the fan specifically to create more mass flow and to create more exit velocity, which is signified here by changing the blue arrow into the red arrow. Yeah? And as you know, Mr. Newton has decided that if we increase whatever goes out the back, we have a more increase in whatever we need in the front. And that holds true. So the result that we get after we modify the engine is a lot more thrust. Now what we would like you all to do is to not increase your thrust, keep it at the same level, but throttle back. And that specifically gives the effects that we're after. Lower fuel burn, the engine runs at a lower temperature, there is less stress in all parts of the engine. We increase the safety margins of the operation because the engine is actually built for higher stresses and higher temperatures. But the most important bit is that we save a lot of fuel burn and emissions. So, how did we get there? Why us? We looked where no one else has looked. In history, there are a lot more than 2,000 PhD papers about this subject. A few people came close to what we discovered, but they didn't follow it through. We did, and what we have discovered is now patent pending and our IP. We have flight tested this, and we have flown this on our own business jet. We have flown this on a 737 with the CFM56 engine, and we fly it also on our turboprop aircraft that we use for certification. a technical presentation is nothing without a bit of a graph. So what you're looking at here at the bottom is N1. Yeah? So from 70% all the way to 100% is the percentage of N1 that the engine will set. And the green line that you see is the line that shows you the thrust that the engine will produce at every different piece of the setting of N1. Of course, that's dependent on the conditions of the day. But basically what we do is we move that green line to the left, to that purple dotted line. Right? And that's how we achieve that lower fuel burn, because we get the same thrust at a lower N1. The performance that we are releasing in the engine has always been there, and you pay for it with fuel and temperatures. And our modification on the fan blade releases the performance that previously was not released. What I want to show you next is how we do this in real life, and I'll show you a video of a takeoff in a 737 with one engine modified. The effect that we're after is actually something like the afterburner that you see on the jets, except without all the light and sound show. But the amount of thrust that we make available to your normal jet engines is something like this. The aircraft that we modified had a very good engine and a slightly worse engine. The engine on the left, the one we modified, had a 5% higher fuel burn than the other one, and it had a 22 degrees higher EGT than the other engine. If you're looking at the dials in a minute, keep those numbers in mind as well. And the third thing that was wrong with this engine was a very high vibration. The vibration indications were around 4.5. So what's going to happen is the pilot flying will set thrust on the normal engine, and then he will move the left engine lever to push it into an equal thrust situation. So this is at the takeoff point. It's the engine run-up happening right now. He's looking for the right balance between the fuel levers to have the equal thrust. Once he's satisfied, he releases the brakes and he starts the clock. And you see the vibration in front of the throttle being just under 2, and then before it was 4.5, right? So the takeoff roll is happening now. You'll see the airspeed come alive. He keeps playing with the throttles until the point of V1. He pulls his hand away. And you can see that on the left engine, the indications are lower, less than on the right engine. There he goes. Rotation. Gear comes up. And there we go. Left engine modified. So later in the climb, I took a snapshot at around flight level 250. We're doing, what is it at the time? I forget. If I blow up the engine stack at that moment, this is what it looked like at flight level 250. We see the fuel flow at the bottom. The difference between the dials is 25%, but of course we had the 5% big delta, so it's 30%. EGT is down 112 degrees. Now this airplane is flying with equal thrust. Right? That's the point I would like to make. If you try to do this in the sim, you know, with the throttles like that, you can't hold the airplane in a straight flight. So this is the effect that we're getting on our test flying. So again, no gimmicks, no magic, this is what we do. A little sidestep When I'm talking about 33% of fuel burn across the world, or 33% of emissions to reduce, how much are we actually talking about? And that is a problem. I did quite some research trying to find out what the number is. Nobody really seems to know. So it's guessing time. And I ended up at a number of about 120 billion US gallons that we are burning in 2025. IATA aircraft, the 80% of traffic, takes, 78 billion, which is 80% of commercial air traffic. I've made a guess as far as the military aviation is concerned. Some of that we can help, most of that we cannot help. Our application, our modification to the fan blades only really works for engines with a BPR of around 2.5 and higher. So any lower bypass engine we cannot touch. The global emissions for 2025 are set around 39 gigatons. And if we look at our own aviation burn of 123 billion, that's 3%. So if somebody says aviation is 2% or 4%, I think I took a fairly accurate stab and I'm setting it today at 3%. However, travel is growing by about 4% per year, aggregate rate. On the other hand, we also get more efficient. Our fleet is getting younger and getting more efficient. So let's say that on average we look at 2.5% growth rate per year. Then in 2050 we're looking at anything between 500 and 700 metric tons of CO2 that we have to produce in SAF. Right? We can touch about 87% of all aircraft in the world. There are some areas in the world where we cannot go, there are sanctions, there are issues, so around 87% is what we can do. So we'll reduce that fuel burn by around 34 billion gallons, and then of course 0.325 gigatons of CO2. Now I don't know what that cost is going to be. Bear in mind also that globally, other industries are getting greener faster. So the percentage, the slice of pie of aviation is actually growing over time as well. So the effect over the next few years of our reductions will only become larger. And you see also 737 and A320 flying today is around 38% of that emission. So with two aircraft types modified, we already captured a very large part of the market. We are looking at a 5-year plan to produce around 75 STCs, 75 aircraft engine combinations. And for us, all aircraft models in the world fall into two distinct categories. They are the ones that we can modify straight away, and they are the ones that we need OEM input in terms of changing logic on the onboard computers, which is mostly Airbus, right? The second thing we look at is the cost that we will have to invest in doing these STCs. No airline at the moment is giving us an airplane to play with, so we need to go to market and buy an airplane for the STC. So I've made a graph there as well to sort of give you an idea of what the STC excess costs are. I was talking about 50% more range. Now, if you have a flight dispatch background, if you've done flight planning, you know that if you reduce your fuel burn by a third, you can actually fly a lot longer and a lot further because the fuel fraction becomes less as well. And to put this in perspective, I've produced a payload range diagram for the A321 models. So here's an A321 CEO, and on a typical day with a typical payload of 210 people, it will do around 2,300 miles nautical. Depends, of course, on your fuel policy, depends on the conditions of the day, but this is a number to play with. Now, after the airplane has been modified with our engine modifications, it will fly a lot further, more than 50% further, in fact. That's interesting news for people who have this airplane in their fleet and who would like to use it on longer routes and not be payload limited. And the other interesting bit about this is, when you compare that modified airplane to a nice and shiny new A321 long range, we're coming very close. That's only 10% more. So that's a lot of money you spend on a new airplane when the modification will give you almost the same. Right, so that's significant. And if you take an example like this and translate it to a higher fuel burn scenario like this. Typical A380 burns a lot of fuel, we know. Of course, it depends on how often you fly it, but if you look at those numbers and you see what this airplane will burn roughly per year, could be 10% more, could be 10% less, it doesn't really matter for the example. You give us this airplane for the time of, let's say, an A-check, and we give you what we call the deltaBurn effect, which is a third lower burn, a lot more range, engines that will last forever, less maintenance, etc. And that 1.5 times range. Now, I know one A380 operator who is interested in a lot of range. I think we all know who we talk about. So I made a little exercise here. I looked at the LOPA, at the cabin configuration of the new A350-1000 ULR that Qantas is going to use for Project Sunrise. And I looked at the floor plan of the A380 and I said, you know, let's do another A-check, give these guys the engine modification, give them this special LOPA, which is the same sort of cabin layout that they dreamt up for Sunrise. And on top of that, I can still take 15 tons of cargo and fly all the way to London. I ran the numbers. I even included a ground range of 10,800 miles, which is flying around Russia, as an example. I plugged in a 20-knot headwind on average, and I can still make it on that payload. So this is the effect that we have on aircraft operations in general. Somebody in the Middle East was talking a lot about the A380neo, and he didn't get what he wanted. He can still pick up the phone when we try to call, except we're not going to call it the A380neo anymore. We're calling it the A380 deltaBurn. And we can do this. We just need to certify it. So where are we today? We have a turboprop, and we see that on the turboprop engines, we see the same effect as on the turbofan, because basically the fan is a propeller. And why the turboprop? Two reasons. One, doing the STC on the turboprop educates the authorities about exactly what we're doing. Second, that's all the money we have. We don't have enough to buy a 737 or a CRJ or anything like that. So this is our proof of concept. This is our fashion statement. For this particular operation, we developed a thrust measuring device. Basically, we strap the airplane down to a couple of load cells that are digitally transmitting information to our computers, and we can see exactly how much thrust the engine is producing. And the numbers are interesting. What you see here on this green graph is the different positions of power that we do for a run-up, and then back to idle again. And you see the ground idle, flight idle, all the way to maximum power. We do the same for the modified engine on the right. Now, in one go, you can see that the modified engine is doing a bit more. But exactly how much more and at what torque is the interesting bit. The normal engine will give you 1,860 pounds of thrust at a torque of 1908 on this particular day. Okay? It was in Arizona a hot day, so this is the best we could get out of it. But the other engine does the same thrust for a lot less torque. And then when we push the engine forward all the way, we get a 20% higher thrust at still a much lower torque, meaning the engine has to work a lot less, which equates into less fuel burn, lower temperatures, less stress for the engine. And don't forget, less stress for the prop as well. And this is the numbers. So 45% lower torque for an equal thrust case, and 400 pounds, 21% more thrust, with still 19% less torque than the normal engine. So these are the effects that we are getting in real life on the turboprop. Yeah? And then we're talking ATR, Dash 8, everything. Our roadmap today is pushing this STC. We're hoping to complete the STC by the first quarter of 2026. So that's, let's say, maximum 5 months away. The next step, of course, is the turbofan STC. And at the moment, we will generate the revenues from, we will generate the cost for the STC from revenues from the turboprop STC. Unless, of course, somebody has a nice jet parked somewhere and doesn't need it, and we can borrow it for 6 months, and then you become our partner, and we'll have a great party together. This picture, a selfie from our team. This was half a year ago. We were in the UK in an engine test cell in Gloucestershire. The same engine test cell where they tested the engines of the Concorde. It was a good test. There's a few people in this picture. The first one, the red circle, is our CEO, Peter Ireland, the owner of the IP of what we're doing here. The second circle is a gentleman called Stephen Molloy, who used to work with Rolls-Royce. He was a program director for the Trent 500 and 700 engines. He looked at our testing and he fell off his chair. He just could not believe what we were doing, because he also saw what we did to the engine. The third gentleman is a certifying engineer for EASA. He was there to officially log this test and write a report about it. And then the gentleman with the big camera, he was present as well. This is the report that Andy Lyons, the engineer, wrote. It was an interesting set of series that we did. This is all the logs from the test. The official results were 10.45%. Now, 10.45% for us was a lousy test. Normally we see 30%, so this was really bad. What happened here is that the engine was not set up properly. The engine was in the test cell without the cowlings that we actually needed for the bypass effect. So this is all we got, but this is what we got from a bare engine. Everybody was suitably impressed. Yeah, the modification itself was quite cheap. Charles asked me to say. It's actually, we did the whole modification in 38 minutes. Yeah, and if you want to know how and why, then please come see me after at my desk, and then we can discuss that. But anyway, the work with this type certificate holder of the LF507 engine has directly led to what we're doing now. We just signed an MOU for the first STC with this particular airline. The airline is called Summit Air in Canada. We're going to do the STC for this particular engine with them, and we're also going to do the ATR and Dash 8 aircraft with them. They are operators, and they have given us permission to work with their aircraft. So for us, that's a very big step. It's the first airlines, after 2 years of asking, who are actually going to help us out. For you all, users, what's it going to look like? Okay? If I come to you and say I can reduce your fuel burn by 1/3, the first thing you're going to ask is, how much is that going to cost? We will not sell our product to you, you will lease it. You will lease the STC, you will lease access to the IP, and you will pay us out of your savings after you make the savings. So what we're trying to do is to not put any burden on the users, the airlines and the operators. The product, we will do the installation on the airline. So, like I said, it fits within the A-check. If you have a regular A-check, then you'll see a couple of our guys working around the engines for a couple of hours, and that's it. We also like to do the camo. We will maintain the installation for you. Design life for our modification is from C-check to C-check. And we foresee that the C-check is just a check and nothing more for our modification. A little side step is deltaBurn as a company. Because what we're bringing to the market is quite disruptive, we thought a very long time about the structure of our company. The one thing we want to avoid is that, let's say, a shareholder buys big shares in our company and then through a back door sells the shares to, I don't know, Boeing, Airbus. And then Boeing gets a control, or Airbus gets a control, and they effectively shut the market for the other brand, which is something we want to avoid. And because of that, we have a unique structure. But because we have a unique structure, the regular venture capitalists don't want to invest because they don't get to see their usual pump and dump and IPO and everything. So we've been struggling with that for about 2 years now. And that's why we have decided to move forward and do this as much in our own funding rounds as possible. Still, if an airline wants to join and wants to enter one of our win-win cooperations, then everybody is welcome. For us, it means if no help is forthcoming, we will just do this in an organic, generic way. And you have to wait 2, 3, 4 years longer on your 1/3 fuel burn reduction compared to stepping in now, giving us an airplane, and be part of the journey. We're talking 1/3 of fuel burn reduction. So if any of you know of any alternative technology in the world today that gives us this 1/3 direct reduction, so no accounting gimmick, no SAF gimmick, just real reductions, then please let me know, because I'm not aware of any. I read online that Rolls-Royce spends a lot of money to make the engine 1% better, so I congratulate them with 1%. The other story, of course, is the UltraFan, which is 10% over the XW engine. Ultimately, we foresee that we will license our technology to the engine OEMs so they can use it in their next level designs. They must be thinking about engines for the next 10, 15, 20 years. We can help them with that. But not right now. Today, it remains a retrofit. We're not at the forward fit stage yet. There's one word I like to close out with, which is green mouthing. Now, you all know greenwashing, and the world is full of it. But the one thing that I have experienced over the last 2 years is green mouthing. And with green mouthing, I mean people who talk the talk, but are not doing anything else. So, as an example, IATA, 80% of the global fuel burn. You would think that they would be interested in this technology to help their customers. As they say themselves, we are leading and guiding the industry. Well, they don't even pick up the phone, they don't return your emails. Maybe the number is too big, maybe nobody believes it, but you would expect people like that to at least spend an hour on a call. The worst thing that can happen is it was a lousy hour, but at least you have the information. conferences around the world. Had the big World Aviation Conference, the MRO Conference, the SAF Conference, all these conferences about making the aviation industry greener. The moment you tell them that you have something interesting to tell them, just give us a half hour and we'll tell your public something they would really like to know. No. I either buy myself onto the stage or they're not interested. And that's what I mean with green mouthing. It's not about green at all. It's about the other green. You know, the stuff you put in your pocket. Sorry, that's my rant. We were talking to people in NASA who were involved with the blended wing body aircraft. As you know, that's one of the things they're looking at. And the steering committee member of that particular project told us that, to his knowledge, what we're doing is the biggest change in efficiency of this century. And actually, that is a quote that I 100% subscribe to. If you have any questions, I'm just outside at my desk. I can talk a bit more, and if you have pressing questions, I can answer them now.
Sander, thank you very much. We have one question on the applicant, Sander. It's from an anonymous person. It relates to direct operating costs. Have you done any study outside the fuel savings or the efficiency of house modification and have any impact on greater TOW takeoff weight? Outside of LLP limits, can it also have an impact on lower EGT margin deterioration, and can it still be beneficial? I don't know the answer to that.
Yeah, so once we modify a jet engine, it will run in a derated fashion for the rest of its life. It will never reach the same EGTs again. The LLPs will live a lot longer. How much longer? We don't know yet. That is something we need to discuss with the engine OEM, and that needs to be investigated. In terms of takeoff weights, yes. At the moment, you have issues with higher elevations and higher temperatures. With the modified engine, we can give you sea level rated thrust up to 7,000 to 8,000 feet. And you can get out of Quito on sea level thrust. Of course, you will not be saving the fuel then, because you'll be using every ounce of thrust that you can find. You can climb a lot faster. You can fly a bit faster. I mean, it's up to the airline how they want to use this new opportunity. Do they want to save emissions as much as they can, as much fuel as they can? Or would they use some of this new technology to fly a bit faster or to fly a bit further? So that's an individual choice for an airline or an operator. But yeah, takeoff weights themselves, if today you're flying heavy long sectors and you need every kilo or pound of your maximum certified takeoff weight, that will change. Because your fuel load will go down by a third or more, so you can actually recertify your aircraft to a lower rated takeoff weight and pay less overflight fees as well. Okay?
Yeah, I mean, for the lower EGT, it translates to lower engine maintenance costs and lower noise emissions.
Yeah, there's more to it actually. As we know, there are some engines in the world today that have real temperature stress situations. Half a certain fleet is grounded because of that. The Pratt 4112 engines has always had an issue with fan blade cracking, as an example. One side effect of our modification, something that we have measured, is that the stress inside the fan blade reduces. And that's partly because we change the flow around the fan blade, which creates less of a torquing effect on the fan blade. So your fan blades will live longer or are less subject to stresses. And of course, inside the engine, everything runs 10% cooler or more. So yeah, big changes.
Yeah, maybe a quick question. Thank you for the great presentation. I'm wondering how different the STC process from a non-safety critical system when it comes to your solution. How different it is? What are the challenges? How you're dealing with them? I just wanted to ask that quickly. Thank you.
we're doing a primary aircraft service STC. So we're doing it with the FAA today. We have a 21J organization in the UK as well. We do a lot of briefing with the authorities. We want them to understand what we're doing. And actually the FAA came back to us and said, despite the fact that you're working on the engine and despite the fact that you have these huge results, we actually consider this a minor alteration, because they see that all parameters of the engine are getting better. You know, it becomes a safer machinery, and that's in our favor. The biggest work we have to do is actually on the aircraft itself. You know, amending the flight manual, amending the FCOMS, and doing all that work. You need a complete new set of performance data for your flight planning system and for your FMS. We need to work with OEMs to change some logic in the aircraft. Our biggest issue is go-around, because we now have so much extra thrust available. If somebody is in a go-around situation and without thinking just slams the throttles forward, not in an Airbus, but let's say in a Boeing, you potentially have a max effect. So we need to look at that with the OEM as well and limit the setting of N1 for the go-around. EPR engines, hopefully the EPR will take care of it. If not, that's something that needs to be looked at as well. So those are angles of attack for our work with the authorities. Yeah.
Okay, there aren't any more questions, so Sander, thank you very much indeed.
Thanks.
Okay, we now have our last speaker. He's Maxim Dubovnik, who's the FB manager at Maribor Airlines.